Right now, at this exact moment, a machine the size of a small car is hurtling through interstellar space at 17 kilometers per second. The temperature surrounding it is approximately minus 270 degrees Celsius, 1 degree above absolute zero, the point where matter itself nearly stops moving. And this machine, built with 1970s technology running on less power than a household light bulb, has been out there for 49 years and still hasn't frozen. That single fact should stop you completely, because everything we instinctively believe about cold, about survival, about the limits of engineering, gets quietly dismantled the moment you start asking why. Most people assume Voyager should be a frozen, shattered relic by now. A block of dead metal, entombed in the most hostile environment humanity has ever touched. And on the surface, that assumption feels completely reasonable. Minus 270 degrees Celsius is a number so extreme it barely feels real. It's colder than anything that naturally exists on Earth. Colder than the surface of Pluto. Colder than the dark side of the Moon. So why isn't Voyager 1 frozen solid? Why are its systems, degraded yes, but operational, still transmitting signals across 24 billion kilometers of empty space? The answer begins with understanding something that most people have fundamentally wrong about cold itself. Cold, the way you experience it, is an act of violence. When you step out on a winter morning and feel that sharp bite against your skin, something aggressive is happening at the molecular level. Billions of air molecules, vibrating with kinetic energy, are colliding with your body thousands of times per second. Each collision pulls heat away from your skin. The faster they move, the more heat they strip. The more collisions, the faster your body loses its warmth. That process, conduction, is how cold kills on Earth. And it requires one critical ingredient: matter, something physical to touch you, something to steal from you. Space has almost none of that. In the interstellar void where Voyager 1 travels right now, there are perhaps a few atoms per cubic centimeter. In the room where you're sitting, there are approximately 10 billion molecules per cubic centimeter. The difference between those two numbers is so large that human language doesn't have an intuitive word for it, and that difference changes everything. With so few particles to collide against Voyager's surface, conduction, the primary mechanism of heat loss on Earth, essentially doesn't exist out there. The cold of interstellar space cannot reach out and grab the spacecraft. It cannot strip warmth from the metal the way a January wind strips warmth from your face. Instead, heat escapes through the only mechanism available in a near-perfect vacuum: radiation. Every object warmer than absolute zero radiates energy outward as infrared light. Invisible, silent, traveling at the speed of light in all directions. In space, that's the only way heat bleeds away. And radiation is slow, gradual, patient, manageable. Think of a thermos flask. The vacuum between its inner and outer walls doesn't conduct heat. So your coffee stays hot for hours, not because the thermos generates warmth, but because it has nowhere to lose it quickly. Voyager 1, floating in a vacuum incomparably deeper and more complete than any thermos ever made, operates on the same fundamental principle. The cold doesn't attack, it waits, and if you generate heat faster than radiation can carry it away, you survive. The engineers at NASA's Jet Propulsion Laboratory understood this in the early 1970s when they were designing a spacecraft meant to go where nothing had ever gone. They knew solar panels would be useless. At Jupiter's distance from the Sun, sunlight is already 25 times weaker than at Earth. At Saturn, weaker still. Beyond that, sunlight becomes effectively irrelevant. A faint ghost of energy, nowhere near sufficient to power the instruments that needed to stay alive. So they chose plutonium. Specifically, plutonium-238, one of the most energy-dense and thermally reliable materials humanity has ever used in engineering. Voyager carries 3 radioisotope thermoelectric generators, RTGs, devices that exploit one of nature's most reliable processes: radioactive decay. Plutonium-238 decays spontaneously, releasing alpha particles and, critically, heat. Continuously. Automatically. Without combustion, without moving parts, without a single switch that needs to be thrown. The heat produced flows through thermoelectric converters, materials that generate electricity when one side is hot and the other is cold. The principle is almost absurdly elegant. You take something that's going to decay anyway, and you turn that decay into survival. When Voyager launched in 1977, its RTGs produced approximately 470 watts of electrical power. That's enough to run a few incandescent light bulbs. By any modern standard, it sounds almost embarrassingly modest. But the spacecraft was designed around that constraint, engineered to be so ruthlessly efficient that 470 watts was not just enough. It was sufficient for decades of operation. And the RTGs produced something equally important alongside the electricity, heat. Raw, continuous thermal energy that radiated through Voyager's systems, warming electronics, cables, and instruments that would otherwise drift toward temperatures at which metal contracts, solder cracks, and semiconductor junctions fail catastrophically. The RTGs didn't just power Voyager. They kept it alive in the most literal physical sense. Every circuit that fired, every calculation processed, every signal transmitted produced residual heat of its own, contributing to a closed thermal loop. A small, engineered ecosystem of warmth floating through an infinite freeze. But generating heat is only half the equation. The other half is keeping it. This is where the engineering becomes almost poetic. Voyager 1 is wrapped, every surface, every component, in multilayer insulation, a material known simply as MLI. It looks, at first glance, almost mundane. Thin sheets of mylar and captain, layered together with tiny spacers creating microscopic gaps of near vacuum between each layer. But what it does is remarkable. Each sheet reflects infrared radiation back inward. Each vacuum gap eliminates conduction between layers. Together, they create a thermal barrier so effective that heat loss slows to a crawl, a whisper of energy escaping per hour rather than a flood. Voyager is not just floating in a vacuum. It is wrapped in a material specifically designed to exploit the vacuum, to use the absence of matter as insulation. The spacecraft is its own thermos, its own survival cocoon. Engineered not for a year, not for a decade, but, as it turned out, for half a century. What makes this even more extraordinary is the challenge the engineers had to solve in both directions. Voyager didn't begin its journey in the frozen interstellar void. It began close to the Sun, and it flew past Jupiter and Saturn in environments where the RTGs at full power, combined with solar radiation and the heat of active electronics, created a genuine risk of overheating. The thermal system had to be sophisticated enough to vent excess heat in the warm inner solar system and retain every possible fraction of warmth in the cold outer reaches. Engineers built thermal louvers into the design, bimetallic strips that open automatically when temperatures rise and close when they fall, like mechanical gills responding to the thermal environment without any command from Earth. No software update required. No human intervention. Pure physics doing the engineering work. It functioned near the Sun. It functioned past Neptune. It is still functioning in interstellar space. The elegance of that solution is genuinely difficult to overstate. In August 2012, Voyager 1 crossed the heliopause, the boundary where the Sun's solar wind finally loses the battle against the pressure of interstellar space. It became the first human-made object in history to enter true interstellar space. The moment was not marked by any dramatic event aboard the spacecraft. There was no shudder, no alarm, no visible sign. But the data changed. The flux of solar wind particles dropped sharply. The magnetic field orientation shifted. Cosmic ray levels from galactic sources, particles born in supernova explosions light years away, increased dramatically. Voyager had crossed into a region of space governed not by our sun, but by the rest of the galaxy, and its thermal systems crossed with it, unchanged, uninterrupted, still doing exactly what they were designed to do. The MLI still reflecting, the RTGs still decaying, the thermoelectric converters still generating current. A machine from 1977, operating in a region of space no instrument had ever sampled, performing exactly as designed. But the clock has always been running. Plutonium-238 has a half-life of approximately 87.7 years. Every 87.7 years, half the remaining material decays into stable lead, and the heat output halves with it. The process is slow, but it is completely inexorable. Since launch, Voyager's RTGs have lost roughly 40 to 45% of their original power output. What started at 470 watts now produces somewhere in the range of 240 to 260 watts, declining by approximately 4 watts per year. NASA has managed this decline with a precision bordering on the obsessive. Instruments powered down. Heaters for non-critical components switched off, allowing those components to gradually cool towards temperatures they were never rated for. In some cases, parts of the spacecraft have already experienced temperatures outside their original design specifications. The engineers let them drift cold, calculating that the core, the transmitter, the flight data system, the critical science instruments, could still survive as long as the RTGs produced enough warmth to protect what mattered most. As of 2025, Voyager 1 continues to transmit. But a crisis emerged in late 2023 that briefly suggested the end had arrived early. The flight data system computer began sending back corrupted telemetry, garbled data that made it impossible to know the spacecraft's status. Engineers spent months analyzing the problem across a communication delay of over 22 hours each way. A single message took nearly a day to arrive. The response took another day to return. Working within that impossibly slow dialogue, the team identified a single corrupted memory chip in the flight data system. They devised a workaround, redistributing the affected code across other memory locations, and in April 2024, Voyager 1 began returning usable science data again. 46-year-old spacecraft, 24 billion kilometers away, was debugged. That this was even possible is staggering. That it succeeded is something else entirely. Current projections suggest that sometime between 2025 and 2030, the RTGs will no longer produce sufficient power to run the final science instruments. One by one, they will go dark: the plasma wave science instrument, the magnetic field sensors, the cosmic ray detector. Each shutdown deliberate, managed, chosen. And then, at some point, perhaps within years of when you are watching this, the transmitter itself will lose power. One last signal will leave the spacecraft, traveling at the speed of light across a distance so vast that it will take more than 22 hours to reach Earth. And then nothing. Not an explosion, not a collision, just silence where a signal used to be. But here is the part that truly doesn't let go. Voyager won't stop. When the last system fails, when the warmth finally bleeds away and the electronics freeze and the transmitter goes permanently dark, the spacecraft will still be traveling at 17 kilometers per second. Newton's first law doesn't care about power levels or frozen circuits. An object in motion in the frictionless vacuum of space continues in motion indefinitely. Voyager will drift, silent, frozen, dark, for timescales that make human history feel like a single breath. In approximately 40,000 years, it will pass within 1.6 light-years of a red dwarf star called Gliese, 445 in the constellation Camelopardalis. No civilization alive today will record that moment. There will be no signal, no confirmation. Just a frozen spacecraft, still wrapped in its layers of mylar and captain, drifting past a star it will never reach, carrying a golden record etched with the sounds of a species that briefly looked up, built the best thing it knew how to build, and let it go. The reason Voyager 1 hasn't frozen in 49 years is not luck, it's not accident. It's the consequence of understanding, deeply, precisely, correctly, what cold in space actually means. Not a violent assault of molecules, but a slow, patient radiation of heat into the void. The engineers gave Voyager a heartbeat of decaying plutonium and wrapped it in a thermal cocoon thin enough to seem fragile and strong enough to outlast nearly 5 decades of the most extreme environment a human object has ever inhabited. They balanced the heat budget to within tolerances that still hold today. They built something that didn't just work, it endured. So when the final transmission comes, and it will come, ask yourself what exactly goes silent. Not just a spacecraft, not just a science instrument, not just 1970s engineering floating in the dark. What goes silent is the last physical remnant of a moment when humanity decided that curiosity was worth the cost of building something extraordinary and releasing it forever. Voyager was never meant to last this long. The mission was Jupiter and Saturn. The rest was bonus. 49 years of bonus. And when the silence finally arrives, the only question worth sitting with is this: if we could build something that enduring, that resilient, that quietly magnificent with 1970s technology, what are we capable of building now if we decide the universe is still worth reaching for? Subscribe and tell me in the comments, when Voyager finally goes silent, do you think it ends something or begins something?